Hey everyone, so today in class we're going to talk about a really cool kind of power series called Taylor series. And Taylor series basically is an example of a specific kind of power series that's actually a recipe for finding the power series representation of differentiable functions. So what we're really going to talk about is the following kind of objectives for the day. We're going to try and be able to represent functions as power series. This is going to be using our Taylor series recipe. So it's going to be things like sines, cosines, exponentials, and some other functions. We'll see that there's two basically variations of Taylor series types ideas. The second kind, called Maclaurin series, actually is just a Taylor series itself, but centered at x equals 0. So we're mostly going to be talking about Maclaurin series today, actually, a special kind of Taylor series. Then what we're going to do is try to derive the Taylor series of other functions from those that we already know. So this is going to be a lot of manipulating Taylor series we already know to generate other Taylor series for not a lot of effort. And the last thing we're going to ask ourselves as well, if we know a Taylor series for a specific kind of function, how can we use that information to know what other series converge to? So we're going to go in reverse. If we know this series, what Taylor series is it actually showing us? And then what function is it always or also connected to? So a few little key points I'll point out in this video in regards to Taylor series is what we're really trying to do today is saying, you know what? If I come up with a function, say any old function that is differentiable, and I wanted to represent this thing as a power series. So we have some coefficient plus the second term of that series, another coefficient times x minus a, the point in which that power series is centered, plus another coefficient times x minus a squared. And we can go on and do this all day if we wanted to. So this is just basically a general power series representation for some function. And what Taylor series is actually allowing us to do is say, you know what? If I want to figure out the Taylor series or power series for a sine, for an exponential, for a cosine, it's going to give me a way to pick out what these C0, C1, C2, C3, all of those coefficients actually are. So what Taylor series is doing for us is giving us the values of those coefficients in front of those x polynomial terms for our series. And the recipe for us is going to be the following. Is if we wanted to write any of those coefficients in particular, so for example, say we have the nth coefficient, what we actually do to compute that nth coefficient is we take our function that we're starting with. In this case, we're just calling that some general function, f of x. We're taking that function and we're computing the nth derivative of that function and evaluating it at the value of a. So again, the a is the point at which our power series is centered at. We're evaluating that nth derivative at a, and then lastly, dividing by n factorial. So again, if we're looking for the coefficient Cn, so that would be like the nth coefficient of our series, we take our function that we started with, that we care to find its power series for, we take the nth derivative of that, evaluate it at the point our power series is centered at, and that is going to be our choice, and we divide it by n factorial. So at the end of the day, what this Taylor series recipe really looks like for us, we take our function f of x, and writing this in a very compactified form, this is going to be the series from n equals 0 to infinity of that coefficient we just talked about here. Where we zoom into this, this is going to be the nth derivative of our function that we started with, evaluated at that point we wish to center our power series, and we divide it by n factorial. But the last thing we need to remember is the dependence on x. So again, this is times x minus the point in which we're centering that series, that quantity raised to the nth power. And that is really our recipe here for Taylor series. So we're going to show where this recipe actually comes from, as well as present some of the popular kind of Taylor series or Maclaurin series that we should know, commit to memory, and love. So the last thing I'll do here is just write out these terms, or the first couple terms of this Taylor series, just in general. So this will just be highlighting that piece that we found up above for us. So again, this is the 0th derivative of our function for the C0 term, and 0 derivative, that's just the function itself, evaluated at A. So this term is just f of that point we centered at, A. We divide it by n factorial. In this case, n is 0. That's 0 factorial, which is 1. Then we add to it the next term of the series, which is the C1 term, which means we take our function we started with, take one derivative of it, and then evaluate it at the point we centered, which is A, all over 1 factorial. And the last thing we do is not forget about that x dependence. We multiply by x minus the point we centered at, and raise to the first power. And we would keep doing this for the other terms, the next term being the C2 term, which means we take our function we started with, take 2 derivatives of it, and evaluate it at that point A, divide it by 2 factorial, and then multiply by x minus A to the power of 2. And we could keep going on and on all day, but as we'll see in class, for many of the Taylor series that we'll actually compute, we'll see a pattern start forming in what these coefficients are. So check out those videos too.